In this lecture, we're going to discuss successive ionization energies, and previously the factors that we have discussed. We're going to include all those factors and determine how ionization energies are going to vary in a particular atom. And I've taken sodium as an example, where sodium has 11 protons and 12 neutrons. So there are 11 protons in the nucleus which are attracting these 11 electrons. Now, successive ionization energy means that I'm going to remove the first electron from sodium. So that's removing one electron. It's going to form Na 1 plus. So that's your first ionization energy. So that's your first ionization energy. The second ionization energy would be that I again take sodium, and I've already removed one electron. I'm going to remove another electron from this sodium, and it's going to form Na2 plus. And remember, these are all gaseous ions. I'm not writing down states, but you should be writing down states when you write these equations. So that's your second ionization energy, where I stands for ionization, E stands for energy, and so on and so forth. I'm going to remove another electron, and now sodium is 2 plus, and I remove another electron, and it becomes Na 3 positive, and that's my third ionization energy, and so on and so forth. In total, sodium is going to have, if I keep on doing this, so in total sodium is going to have 11 ionization energies, which means that sodium has a total of 11 electrons. So if I remove the 11th electron, that equation would be, the 11th ionization energy would be that sodium has a 10 plus charge, which means that 10 electrons have been removed, and I'm removing another electron, and now it's going to be sodium 11 plus. That means all its electrons are gone. That's my 11th ionization energy. Now I'm going to compare and see how these ionization energies are going to vary from first to the 11th. So I'm going to remove one electron one at a time from the sodium atom and see whether the energy required is going to increase or decrease, or whether it's going to stay the same, and how the factors that affect ionization energy are going to affect these successive ionization energies. Now I've drawn this graph for you, and the y-axis of this graph represents ionization energy, and the x-axis represents the number of the ionization energy. So that's first, then second, then third, then fourth, and we're going to have a total of, this is going to be the 11th ionization energy. So we have a total of 11 ionization energies. So my x-axis represents the number of the ionization energy, and the y-axis represents the amount of ionization energy, whether it's high or low. So when I remove the first electron, and I'm going to start with the first electron, so I'm going to mark this electron. So that's my first electron. I'm crossing it out. I'm removing that first electron. Now that first electron would have the lowest ionization energy. The reason being that it's far away from the nucleus, so it's really, really far away, and it has the highest amount of shielding. So the first ionization energy is going to be the lowest. It's going to be the easiest to remove an electron. But as I move to the second ionization energy, if I try to remove the second electron, there's going to be a big noticeable jump in the ionization energy, and the reason being that as you move from the first to the second, so shielding is going to decrease because you have now less, it's getting closer to the nucleus. So shielding decreases, and distance decreases as well, because now the electron, this second electron over here, it's really close to the nucleus compared to the first one. So distance decreases as well. And the third factor is that the positive charge on the ion increases, because now when you're removing the second electron, you're removing an electron from an atom that already has a +1 charge. It already has one electron removed. So there are three factors that would say that now it's going to become more difficult to remove an electron. So the ionization energy is going to drastically increase. Now, as I remove the third electron, and the fourth electron, and the fifth electron, and the sixth, and the seventh, and the eighth, and the ninth, so up to ninth ionization energy, there's going to be a very slight gradual increase in the ionization energies. So that's my sixth, then I have my seventh, and then I have my eighth and the ninth. So there is a very slight gradual increase in ionization energies, and the reason for that is that as you remove all these electrons, the shielding remains constant. If you're removing the electrons from the second shell, now the shielding remains constant. That's one factor. There's no difference in the factor. The nuclear charge is always constant. You're removing the electron from a sodium atom, so the nucleus has +11 throughout. It's not going to change. So the nuclear charge doesn't change. The distance is going to remain the same. All these electrons would be exactly, or probably they would have similar distances from the nucleus. So there wouldn't be much difference in the distance as well. There's only one factor that's changing, and that is that the positive charge on the ion, increases. So as the positive charge on ion increases, that's the only factor that's changing. So the ionization energies keep on increasing. So you're removing an electron. If you're removing the third electron, then the positive charge is 2+. If you're removing the fourth electron, the charge on the ion is 3+. So the positive charge keeps on increasing. So it's going to become slightly more difficult. But there's only one factor that's changing. So based on that one factor, the ionization energy is not going to drastically increase, but it's going to gradually increase. But as you move to the 10th and the 11th electron, let me mark them with a different color. So as you move and try to remove these 10th and 11th electrons, now these are again, there's going to be a jump again. And the reason for that jump is again the same. That as you remove the 10th electron, again you're now, there's one shell less. Now you're closer to the nucleus. So now again the three factors kick in. One is that shielding decreases. You are now closer to the nucleus. There's less hurdle between the nucleus and the electrons. So shielding decreases, distance decreases. And the third factor is that the positive charge on the ion increases. So that increases. So all these three factors would say that the ionization energies of the 10th electron, removing the 10th electron over here, it's going to be greater. And it's going to be drastically greater because there are three factors which are suggesting that ionization energy should increase. So removing the 10th and 11th electron is going to be extremely difficult. So there's going to be a jump in ionization energy. So whenever you move a shell, there's always going to be a jump in ionization energy because you're going to get closer to the nucleus, and there would be less shells between the electrons and the nucleus. So and when we talk about the 11th and when we compare the 10th and the 11th ionization energy, so between the 10th and the 11th, the shielding and the distance are approximately the same. So there's only one factor which is positive charge on ion. So the 11th is only going to be slightly greater compared to 10th, because there's only one factor suggesting that the 11th is going to be having a higher ionization energy, which is the positive charge on the ion. So that's how you're going to sketch a graph for successive ionization energies. I'm now going to do another example of successive ionization energy, and this time I'm going to take the example of fluorine. And in successive ionization energy, I'm going to continuously remove electrons from a gaseous atom of fluorine. So I'm going to remove the first electron, that would be the first ionization energy. Then I'm going to remove the second electron, that would be the second ionization energy, and so on and so forth. In total, there would be 9 successive ionization energies in fluorine, because fluorine only has 9 electrons. So removing the first electron, I'm going to start off with this one, so let's cut that out. Removing the first electron, it's going to be the easiest. So that's going to be the easiest one. So the ionization energy for that would be the least amount of energy would be required to remove that electron, and the reason is that it's really far away from the nucleus, and it has more shielding, plus you're removing it from a neutral atom, so removing that electron is going to be very easy. Then I remove the second electron. Now when I remove the second electron, there's going to be a very slight increase in ionization energy, and the reason is that now so I've removed let me write the equation. I've removed 1 electron from a gaseous atom of fluorine to get fluorine 1 plus, which is also going to be gaseous. Now that's my first ionization energy. Now if I remove the second electron, so the second electron would be removed from a gaseous 1 plus ion, because the first electron has already been removed, and I'm removing the second electron, and it's going to produce a 2 positive ion. So fluorine is going to have a 2 positive charge. So that's my second ionization energy, and so on and so forth until I've removed all the 9 electrons. So the second ionization energy is going to be slightly higher, and the reason being that once I remove the second electron, there's going to be a +1 charge on the fluorine atom, so it's going to become an ion. So I'm going to remove an electron from an ion, so it's going to become slightly more difficult. The shielding remains the same, the distance remains exactly the same, the nuclear charge remains the same, so all the other factors are constant. Similarly, removing the third electron, there's going to be a slight gradual increase in ionization energy, because nothing has changed except for the positive charge on the ion. So in a similar way, I remove the fourth electron. So the fourth electron is removed, then I remove the fifth electron, and again there's a slight increase because the positive charge on the ion is increasing. So I remove the sixth and the seventh electron. So my sixth and seventh ionization energy, there's going to be a gradual increase in ionization energies, and the reason being that the positive charge on ion increases as I keep on removing electrons. All the other factors remain almost constant. Now what's going to happen if I remove the inner electrons? Now I'm moved to the 8th electron and the 9th electron. When I remove the 8th electron, there's going to be a jump in ionization energies, and the reason for that drastic jump is that now the electron is closer to the nucleus, so distance decreases, and it's now one shell closer to the nucleus, so shielding is going to decrease. Now there's less. Now the proton and the electrons are now directly inside of each other, so there's going to be more attraction. There's nothing in the middle, so shielding decreases, and the positive charge on ion is increasing. That's a factor that's constant throughout. As you keep on removing electrons, the positive charge on ion keeps on increasing. So because of these three factors, there's going to be a drastic jump in ionization energies. And then I remove the last electron. Now the last electron compared to the 8th electron, it's going to be a slight gradual increase. The reason being, again, that when you compare the 8th and the 9th electron, the only difference between the two is that the positive charge on ion is going to be greater. So there's only going to be a gradual increase. So there's going to be a jump that you'll experience when you remove the 8th electron. Removing the 8th electron from the inner shell is going to be a lot more difficult. So that's how the successive ionization energy graph for fluorine is going to look like. In this example, we're going to study the successive ionization energy of aluminium. Now, aluminium has 13 ionization energies. It has a total of 13 electrons. So you remove the first, then you remove the second, and eventually you're going to remove 13 electrons. So aluminium is going to have 13 successive ionization energies. The first one is going to be you remove an electron from an aluminium atom and you get an aluminium positive ion, and they would be gaseous. The second would be that once aluminium positive has been formed, +1 gaseous, and you're going to remove another electron and you're going to get aluminium 2 plus gaseous, and so on and so forth. You're going to remove a total of 13 electrons. So the ionization energies are going to be 13. There would be first, second, third, fourth, and then eventually up to 13. So you'll have 13 ionization energies. And now I'm going to remove an electron one by one. So if I remove the first electron, let's say this is the first electron, it's furthest away from the nucleus. So this ionization energy would be the smallest, the least amount of energy would be required to remove this electron. It's really far away, the distance is great, the shielding is more, and the positive charge, there's no positive charge on the atom, so it's the easiest to remove an electron would be the first one. If I remove the second electron, now the second electron has all the other factors are almost the same, the distance is the same, and the shielding is the same. The only factor that matters is that the positive charge on ion is increasing. So the second is going to be slightly higher than the first one. Then I remove the third electron, which is this one. If I remove this third electron, then again everything is exactly the same, the shielding is the same, the distance is the same. The only factor that's counting is the positive charge on the ion is increasing. So the first three ionization energies would have a gradual increase. But once I move to the inner shell and I remove the fourth electron, now there's going to be a drastic jump in ionization energies, and the reason being that now the electron is closer to the nucleus, there's less shielding, and the positive charge on ion is greater. So there's going to be a drastic increase in attraction between the electron and the nucleus, so you would require a lot more energy to remove that electron. So this is where the jump is going to happen. So again, the distance of the fourth electron is lesser, and there's less shielding, and the fourth point is that the positive charge on ion increases. Now all these three factors point to the fact that ionization energy should increase. So it increases drastically because there are three factors that we need to account for. Now if I remove the fifth electron or the sixth electron or the seventh or the 8th, 9th, 10th or 11th, there's going to be a gradual increase in ionization energy. So let me plot that. If I remove the sixth electron, then the seventh electron, then the 8th and the 9th and the 10th and the 11th. Now all these electrons, they belong to the same shell, which means that the shielding is the same and the distance is approximately the same. So the only factor that's counting is this positive charge on ion keeps on increasing. So as you keep on removing electrons, the atom becomes more and more positively charged. So that's the only factor that makes it more difficult to remove an electron. So positive charge on ion, that's the only factor that continuously increases. Now I move to the last shell, which is this one over here, these two electrons. Now removing these two electrons, this would be the 12th and 13th ionization energy. So there's going to be a jump again when you're removing these two electrons. So there's going to be a drastic jump again, and the same factors are going to account for that, because now these two electrons are closer to the nucleus and there's less shielding and the positive charge on ion is greater. So removing these two electrons would be difficult. And the reason why the 13th ionization energy is greater than compared to the 12th is that the positive charge on ion keeps on increasing. So that's how your graph is going to look like, and there would be two jumps when we talk about the successive ionization energies for aluminium. Now this is another type of question that you can get on successive ionization energies. What they would give you is, instead of drawing a graph, what they would give you is, they would give you successive ionization energies of a particular atom. In this case I'm talking about aluminium. So he's given you that the first ionization energy of aluminium, that's 577 kilojoules per mole, and the second one is 1820. The third one is 2740, and the fourth one is 11,600. So and so on. They can give you, they can quote further ionization energies as well. Now, what the question is going to look like is they're going to ask you that they would assume that you don't know whether this is aluminium or not, and they would give you different options. Now, for example, they can ask you in which group of the periodic table is this particular element. So, if you look at the ionization energies, removing the first electron, it's easy because it's further away from it's the farthest away from the nucleus. The second electron, there's a slight increase in ionization energies because of the positive charge on the ion that's increasing. Then removing the third electron, that's also slightly higher. But as you move to the fourth electron, when you try to remove the fourth electron, there's a drastic jump in ionization energies. It jumps to 11,600. So there were approximate differences of 1,000 or around 1,000 kilojoules between the first and the second and the third. But between the third and the fourth, there's a huge massive jump of almost 4 times when you move to the fourth ionization energy, which basically suggests, it's going to suggest that this particular electron, this one, it's removed from an inner shell. Electron is removed from an inner shell. The reason is because the electrons have, the ionization energy has a sudden jump. So removing the first electron, that was easy. Removing the second was easy as well. The third was easy as well. But as soon as you move to the fourth electron, now you're closer to the nucleus, there's less shielding, and the positive charge on the ion is increasing as well. So there are 3 factors that would suggest that this particular ionization energy over here is for an electron that's closer to the nucleus, which would suggest that these first 3 electrons, these were probably in the outermost shell. So these were the outer electrons. So remember, the jumps basically suggest that you're moving closer to the atom. So you can get questions on this, which would be they could ask you about which group this atom is. So this has 3 outer electrons. The first, second, and removing the third electron were easy. That means that the outermost shell had 3 electrons. So this element is probably in group 3. I'm assuming that we don't know whether this is aluminium or not. I've quoted values for aluminium. Or they can ask you about identifying the element. They can give you different options, and you would have to look for an element that is found in group 3, because all group 3 elements are going to have the exact same trend. The first ionization energy would be less, the second and the third would be slightly higher, but the fourth there's going to be a drastic jump in the fourth ionization energy. So remember, this jump can give you information about how many electrons there are in the outermost shell of an atom.